And now let me introduce our first speaker, Dr. Russell Qualls. Dr. Qualls has served as an extension specialist at the state climatologist of Idaho at the University of Idaho in Moscow, Idaho, since 2000. He is a licensed professional engineer and conducts research as a hydrologist and climatologist. Specifically, his research focuses on satellite remote sensing of mountain snowpack, snowmelt runoff modeling, and land surface evaporation modeling at regional scales. He applies this research for the benefit of agricultural irrigation with a variety of government agencies and other stakeholders. Russ, it is with great pleasure that we welcome you to today's webinar. We very much look forward to your comments on the 2021 Snow and Water Outlook. Please go ahead with your presentation.
Thank you for joining me today to talk about Western snowpack. As much as 75% of Western water supply comes from mountain snowpack, and much of this is used for irrigation. Okay, a map of the mean annual precipitation across the U.S. reveals the importance of mountain snowpack for agriculture and irrigation in the West. The West has greater spatial variability and spans a wider range of precipitation than does the eastern U.S. For hydrologic reasons, much of the precipitation is concentrated in the mountainous areas, specifically the Pacific coastal mountains and the Rockies, which in themselves are unsuitable for agriculture and occupy a small fraction of the total land area. Consequently, much of the agriculture is carried out in areas with minimal local precipitation, that is, arid and semi-arid areas. For example, the Snake River Plain of southern Idaho, the Columbia Basin of eastern Washington, and the Central Valley of California. Two primary essential ingredients for plant growth are sunlight and water, and semi-arid areas with upstream mountain snowpack have both. Okay, in addition to topographically induced variability, a large fraction of winter snowpack accumulates from a small number of winter storms, mostly off the Pacific. The stochastic nature of these storms, how many and when and where they arrive or don't arrive, accounts for the waxing and waning of drought and the migration of drought from one area to another across the West. The U.S. Drought Monitor quantifies and tracks drought across the U.S. These two maps show the present drought conditions with the right being the present and the conditions 1 year ago on the left. Drought is classified by degrees of severity ranging from D0, which are abnormally dry conditions in yellow, to D4 or exceptional drought in the dark brown. White represents the absence of drought. The right image shows that drought has significantly intensified in severity and areal extent during the past year, especially in the Southwest. These graphs show time series of percent areal extent of each drought category from 2000 to the present for the 6 major river basins or regions of the West. Westwide, drought groups temporally, although with differing severity across the region. Much of the past 20 years has been affected by drought. You can see here that 2000 to 2005, 2000 to 2011, 2012 to 2016, 2018, and mid-2020 to the present have all been significant periods of drought. Depending on its duration, the present drought on the right-hand side of the screen may turn out to be among the most severe in degree and severity and spatial coverage. Let's turn our attention to the snowpack, which is a significant influencer of drought. The National Operational Hydrologic Remote Sensing Center runs a daily national snow model and map for NOAA at 1 kilometer resolution. The model assimilates data from a variety of background and satellite-based observations. This map from earlier this week shows the model's spatial distribution of snow water equivalent across the Pacific Northwest. Snow water equivalent, or SWE, represents the equivalent liquid depth of a melted sample of snow observed or modeled. It's important because it represents the actual amount of water present in the snowpack, which is available to melt and become stream flow. Let's take a look at some of the actual field observations of snow. The NRCS operates a collection of ground-based snow telemetry stations, or SNOTEL stations, across the West. These transmit data automatically to a central server so that SWE can be monitored throughout the snow season. Many have been in operation since around 1980 or for about 40 years. Each circle on this map identifies a single snow-tail station. Snow accumulates throughout the winter, reaches a peak in the spring, and then begins to melt. The color of each circle on this map represents the median annual peak snow water equivalent for each station. Dark blues are the highest, or sometimes in greater than 50 inches, decreasing down through the greens and then mustard to white, which is 0. Not surprisingly, based on PRISM, the PRISM mean annual precipitation map, the coastal mountains and northern interior mountains exhibit the highest median SWE. If we look at the present SWE values, noting that peak annual SWE often occurs in April, we see a distribution similar to the median peak SWE that I showed earlier, but possibly a little bit lower in magnitude in many areas. Drought in a particular area is defined for that region being drier than average for that area. So we need to compare each station with its own historical record. This map ranks each station's present, which is near peak SWE, with its own period of record peak SWE. White circles in this case represent the median. Cool colors, green to blue, are stations whose present SWE percentile is above the median, and warm colors, that is peach through red, have present SWE percentiles increasingly lower than the median. You can see here that most of the West is significantly lower than the median, except for the northwest corner of the Pacific Northwest. By comparison, 2020, as shown here, the snowpack was largely above the median, except for California and a few concentrated pockets like the south central mountains of Idaho. One thing we can take a look at is the number of 2021 stations that set new historical records for peak SWE, with highest or second highest represented by blue and green respectively, and the lowest or second lowest represented by red and orange respectively. A few records have been set in 2021 almost exclusively on the low end, or in other words, low records so far. We can compare this with 2015, a period of significant drought that we saw earlier on that U.S. Drought Monitor time series. Significantly more record lows were set in 2015 than this year. Nevertheless, the percentiles for peak snow water equivalent in 2021 are still quite low and concerning. As a real quick contrast here, 1997 was a year of very high snowfall, and there were a number of high records set that year. And in fact, a world record snowfall was set at Mount Baker Ski Resort that year with more than 97 feet of snowfall, so that's snow depth rather than snow water equivalent, that was recorded that year. Now, we can aggregate snow-tail observations by sub-basin or river basin. And if we take the ratio of the percentage of SWE to the percentage of cumulative precipitation, we can see how successful or efficient the basin has been. So in this image, the left-hand slide represents the present snow water equivalent ratio with respect to the median peak snow water equivalent, and the right side image represents the cumulative water year precipitation with respect to the 1981 to 2000 median. And so, as I was saying, if we take the ratio of the values in the corresponding basins here, such as looking at the upper left-hand corner, the basin with 135% of average or percent of median for SWE versus the 110% of median annual precipitation, the ratio of those is 1.23. And what this indicates is that that upper basin was relatively successful in accruing precipitation and storing it as snow water equivalent rather than having it melt off and run off. Now, if we look at the lower right corner, we see the opposite has occurred there. The annual precipitation has been low. It's only about 50% above average if you see the precipitation map on the lower right. But the amount of SWE that has been stored compared to its median value is only 46%. So the ratio of those two is about 85%. So in other words, that basin has been actually relatively unsuccessful in storing the meager amount of annual precipitation that has occurred as snow water equivalent. So the gradient between these two from the northwest down to the southeastern corner of the southwest is it indicative of increasing drought in the southwest relative to the northwest. All right, I want to just briefly mention for low elevation stations observations, there's a volunteer precipitation observer network that was started in Colorado in 1997 at the Colorado Climate Center called COCORAS. And the reason I mention this is primarily that this creates a great opportunity for those of you who are extension personnel to advertise and recruit volunteers. So the observations that are daily collected by each observer can be entered online, and they get recorded in near real time, so you can see the values, and you can see the great comparison that shows up between across the nation as these data values come in. So I want to turn now to look at some weather outlook information. This is data that was prepared by the Climate Prediction Center, and we'll look at the present through the summer and into the fall. So the first slide here takes a look at the forecast or the outlook for just the current month. And I'll use this to kind of describe a little bit about what these images represent. So in each slide that we look at, the left-hand slide will represent temperature, and the right-hand side will represent the precipitation. And the values present here are indicated by A representing above average for the particular variable temperature or precipitation, so a likelihood during that month of temperatures or precipitation being above average, and B represents the likelihood that those values will be, for the respective variables, will be below average. And the numerical values represent the percent likelihood of it being above or below average. Okay, so what I've got here is we're going to shift and look at a number of seasonal outlooks going through, progressing on a 1 month increment through this summer and fall. So that it's a 3 month or one season outlook, but we're going to march 1 month at a time through this. So what you see here is for April, May, June, so for this spring, you see that the temperatures are likely to be above average, and that's kind of expanding across the west and actually is also present across the east, with the exception of the upper corner of the northwest. And on the right-hand side, precipitation is likely to be below average, kind of following this northwest to southeast trajectory across the basin. Then for May, June, and July, and by the way, some of these I have a 2020 written here. The data is actually from 2021. What you see is the kind of expanding of and increasing the likelihood of above average temperatures throughout the west, especially in the southwest, and propagation of these below average precipitation moving into the northern part of the region and increasing in intensity. And continuing this here, we see that pretty much the whole U.S. by midsummer is going to be engulfed in a high likelihood of above average temperatures, and particularly that big bullseye of very high likelihood in the southwest. And at the same time, precipitation in the northern part of the west is still remaining below average. I didn't mention earlier, but EC stands for equal chances, meaning that there are equal chances of above normal or below average conditions. And one of the things you do see in this image is that there's beginning to be a little bit of a increase of above average likelihood of precipitation kind of sneaking into the southern portion of Arizona. All right, and this pattern generally is kind of continuing, a little bit of that precipitation increase across Arizona, propagating northward. And you begin to see that late this summer that the below average precip is going to begin to migrate a little bit to the east, and there's a little bit of a backing off with somewhat of a lowering of the likelihood of above average temperatures, but still the whole west is likely, highly likely to be above average in temperature through the summer. And then again, kind of a similar pattern here as seen throughout the earlier part of the summer. So if we kind of summarize what we've seen here, these outlooks show conditions of above average temperature through most of the West, and in some areas very significant likelihood of above average temperatures, and some areas below average in precip, with a little bit of above average precip sneaking into Arizona later in the season. And so collectively, these suggest potentially increasing drought severity throughout the summer. Okay, so let me kind of wrap this up. The three main things that we've looked at were the drought monitor, and then the SNOTEL data, and then the Climate Prediction Center outlooks. So if we take a look again at the U.S. drought monitor, we see this strong, exceptional drought pervasive across the Southwest. California is entirely in drought, although not quite as severe as say, Utah, Arizona, and New Mexico, and Nevada. But still, the entire state is engulfed in drought, and a little bit of a reprieve in the upper corner of the Pacific Northwest. So what we see is that there's significant widespread drought, especially in the Southwest, and that snowpack and precipitation from the SNOTEL data were shown to be moderately low or low, except for that upper corner of the Pacific Northwest, which kind of explains the lack of drought in the corner of Washington State. But the Climate Prediction Center outlooks show likelihood of above average temperatures and below average precipitation for much of the West, continuing from the spring into the summer and the late fall. So collectively, as I noted a moment ago, these snow conditions and the seasonal outlook suggest that the drought severity is likely to persist or increase, especially in the Southwest. And there are possible impacts to irrigation resulting from these that depend really a lot on local regulations for a given irrigator, as well as on the seniority of water rights and the sources of water. All right, that's what I have to present. The next slide just reiterates the sources of information here, and I'm going to be sending a PDF to the host to post on the Ag in Uncertain Times website if anybody has an interest in looking at sources of these data after the fact. Thank you very much.
Thank you, Russ, for that excellent presentation. Lots of good and thought-provoking information there. We will turn now to our next presenter, but before we do, let me remind all of our attendees that you can type any questions you have for Russ into the chat window, and be sure to hit the submit button once you do that, so that we can get those answered during the Q&A session at the end after our next speaker.